Thank you everybody for joining today. My name's Sandra. I am with the UC Davis Air Quality Research Center. I am happy to have Dr. Carl Malings to join us today for our webinar. This webinar is a continuation of some of the Air Sensors International Conference presentations that happened in May of this year in California, as well as we had several presentations in India, Bangalore, India in August. So we're excited to continue the discussion on air quality sensors and have Dr. Malings join us. So he has been a assistant research scientist at NASA Goddard Space Flight Center, working under the JSTAR 2 cooperative agreement since April 2022. Prior to that, he was a postdoc fellow at NASA since April of 2022. His research focuses on integrating air quality data from numerous sources, including models, satellites, regulatory monitors, and low-cost air sensors to develop more comprehensive assessments of air quality. His prior research experience, he has prior research experience in low-cost sensors from air quality monitoring, conducted at CMU and the French National Research Agency. He received his PhD in civil engineering infrastructure systems and monitoring optimization from CMU in 2017. Thank you so much for joining us. I am excited to hear about your presentation, so I'll let you go ahead and take it away from here.
All right. Yeah, thanks, Sandra. So today, I guess it'll sort of be a follow-on to my presentation at ASIC, but also a little bit of new material. And the general idea is to give an overview and a little bit of discussion on satellites, low-cost sensors, and the opportunities for using them together to improve our understanding of air quality. I think let me just check. So with this presentation, the idea is that for it to be a little bit more higher level of a discussion without going into too much technical detail. So hopefully, even if you weren't able to attend to the ASIC talks or things, you'll still be able to kind of follow along. And I will try to keep my eye on the chat and on the windows in case people have questions. You can put your questions in the chat, and I'll try to answer them as we go through. My tentative plan here is to spend about half the time going through this presentation, and then leave a good chunk of time at the end for questions and more open discussion with people on this topic. So getting started, let me go to okay, so hopefully everyone can see the slides. The general plan is I'm going to start off with a brief kind of introduction or recap to low-cost sensors for air quality and what their advantages or disadvantages are. Again, if you've been to a lot of the ASIC sessions, you probably know you've heard basically everything I'm going to be talking about on that front already. But just to recap, so everyone's on the same page, I'm going to be spending a little bit more time on satellite information for air quality. That's something people might not be as familiar with. So I'll try to give a general, again, a high-level overview of what the capabilities and what the limitations are for using satellite information to inform us about air quality. And then the bulk of the presentation, I'll be talking about some of the opportunities and also the challenges of using these two different data sources together and how they can complement each other and what kind of things can be done on that front. So starting off with, so low-cost sensors for air quality. Again, that was sort of the topic for ASIC. So hopefully, people are broadly familiar with these. But again, just to keep everyone on the same page, the basic idea is that these instruments can make measurements of air quality at a very local level. And the key difference from traditional instruments, which is what's in the name, is they're lower cost compared to these traditional instruments. And they typically achieve those lower costs by using different measurement technologies, which are less expensive to implement. There are a wide range of different technologies that fall under the general umbrella of low-cost sensor technologies. I have a couple examples here on the screen, but of course there are many more. And they measure various things. I think at a basic level, most of these low-cost sensor devices are measuring at least particulate matter pollution, usually in the form of PM2.5. That's particulate matter with aerodynamic diameter of 2.5 microns or smaller. Along with, typically most of these sensors also measure temperature and humidity, which, as you'll see in a couple of slides, that's important things to measure as well when you're measuring particulate matter. But this is sort of like the basic level, and then there are other instruments which include as well gas sensors, typically electrochemical sensors for measuring the concentrations of various gases relevant for air quality, like nitrogen dioxides or other nitrogen oxides, ozone, carbon monoxide, SO2, things like that. So you have sort of these monopollutant sensors, which typically measure, as I said, particulate matter, and multi-pollutant sensors, which measure sort of almost the full range of air quality relevant parameters for most countries. So zooming out to a global level, I think one of the main areas where these low-cost sensors are finding themselves to be very useful is in filling in the global air quality data gap. And there are a lot of ways to sort of illustrate it, but one way I typically use to illustrate it is the figure I have on the slide here. So on the vertical axis, you have the annual average, again, PM2.5 as a proxy for general air quality, but the annual average PM2.5 concentrations, these are sort of estimates. And I'll talk again a little bit more about that later, how those estimates are derived, but these are estimates. And I've sort of broken it down by different regions of the world. And on the horizontal axis, you have the density of PM2.5 monitors per million people. In the triangles, I'm plotting the density if you only consider the sort of traditional or regulatory grade instruments. And with the circles, I'm showing the density if you also include low-cost sensors. And this plot is actually a little bit out of date. I need to update it at some point, but I think it still illustrates the general points. First off, there's sort of this inverse trend there where regions around the world which tend to have higher annual average concentrations of PM2.5 tend to have fewer monitors per capita. And then the other major thing, which is the most relevant for this presentation, is the difference in monitoring density when you start considering these low-cost sensors as well as the regulatory sensors. And if you notice that the horizontal axis is on a log scale, you can see that in some areas of the world, this is an order of magnitude more monitors per capita than is available with traditional instruments. And that's only that sort of gap, or that difference is only becoming greater over time. So overall, the idea is that these low-cost sensors are really filling a niche in terms of filling in gaps in air quality monitoring around the world, the gaps between the traditional regulatory monitoring networks. So what are the advantages of these low-cost sensors? We've already discussed some of these, but sort of the prime advantage is in the name, the lower cost compared to the more traditional instruments. So that's both in terms of the initial purchase costs of the instruments themselves, could be, typically, orders of magnitude, if not several orders of magnitude less than a comparable reference grade instrument measuring the same things. And that also translates into sort of lower operational costs, typically lower infrastructure requirements in terms of many of these sensors don't necessarily need a stable data network. They can run off of cellular networks where those are available. Many sensors also operate off of solar panels. So they don't necessarily need a stable power grid either. Again, depends on the model, but these are typical advantages that lead people towards using these lower cost sensors. And all of this, as we showed in the previous 2 slides ago, actually, or no, it was just the previous slide. So all this sort of leads into the greater availability of these sensors, which in turn leads to sort of increased availability of the data from these sensors. And also, in certain cases, sort of breaking down the sort of institutional barriers where sometimes agencies that run the more expensive monitors don't necessarily share the data as readily as the data from these low-cost sensors, which is often made publicly available just by default. So in various contexts around the world, this is sort of increasing the democratization, if you will, of air quality data. So yeah, those are sort of the main advantages. And then the last thing on this list I have is the high intersensor consistency. So typically, a lot of the instruments using these sensors are mass produced. And a typical advantage of that process, with some caveats, but the typical advantage is that, with these sensors being mass produced, they tend to operate in a fairly consistent way of sensors from the same manufacturer. So if you were to compare them together in the same location, which is what I'm showing in the figure on this slide, there's sort of a high level of intersensor consistency, at least with sensors of the same type. So that's a sort of an overview of the advantages. But we also, of course, have to acknowledge the disadvantages. And I think a couple of disadvantages I have listed on this slide, low cost does not necessarily mean no cost. There are still some barriers to using or having access to these sensors. So that of course has to be acknowledged. And then I think the main difficulty, which is, if you've got ASIC, a lot of people are working on these difficulties, is the cross sensitivity and the basically the need for calibration for these sensors. So as I mentioned, the way to achieve this low cost of these sensors is that they use different measurement techniques from the regulatory grade instruments. And because they use different measurement techniques, there are discrepancies in data collected by a regulatory instrument versus a low-cost monitor. And under different conditions, those discrepancies can be greater or lesser. And so identifying what those conditions are and figuring out ways to correct for those differences is, I'd say, a major ongoing area of research, which is something that I worked on for several years. And the typical way that this is done is through co-location studies. Basically, a group of low-cost sensors is located in close proximity to a reference monitor for some period of time. Data is collected from both those sets of instruments, and some sort of calibration is created which corrects the data from one instrument, from the low-cost sensors, to better match the regulatory monitors. And that's what I'm kind of illustrating with the figure on the left. You have sort of indicated by the red arrows before calibration, the performance is quite a bit worse than after calibration. Based on those co-location studies, the performance has been increased by quite a bit, and the consistency in the performance has also been improved. But there are several limitations to this as well. Of course, to do this kind of a calibration, you need a reference monitor in place. And as I showed a couple slides ago, depending on where you are in the world, you might have to go quite a ways to find your nearest reference monitor to do these kinds of co-location studies. And depending on that as well, you may not find a reference monitor which is sort of representative of the conditions in which these low-cost sensors are going to be applied in practice. And that's very important because these calibrations you apply can be quite sensitive to the environmental conditions. And I'm sort of illustrating that on a temporal basis with the figures on the right. This is showing two different studies in the US and then in Rwanda, where calibrations developed in certain seasons were highly biased when applied to data collected in other seasons. So on the top you have, let's say, a summer calibration is highly biased when applied to winter data in a US context. Or in Rwanda, we had alternating wet and dry seasons, and calibrations developed during the wet season would perform very poorly in the dry season and vice versa. So, if you just did one co-location study in one area with one and during one season and apply that to the whole year, that might not work very well. And if you went to another region with a slightly different climate, you also might have similar problems. So overall, I would say, this are the key limitations of low-cost sensor, is the need for this sort of locally defined calibration to ensure that the data are of good quality. Okay, so now moving on to the satellite data. So for satellite data for air quality, there are many different instruments, many different satellites, which provide many different types of data which are relevant for air quality. I won't go through sort of an exhaustive list of that today, but I'll try to give a very high-level overview of what are the advantages and limitations of satellite data for air quality. So I think with the advantages, you can kind of see with the illustrations on the picture here. The key advantages are that satellites provide, depending on the satellite and depending on its orbit, either a wide area regional or a global overview of conditions. So you have basically two different types of orbits. There's a geostationary orbit and a polar orbit. Most air quality relevant satellites have been in polar orbits, which means they orbit around the poles of the Earth. And what this allows them to do is basically get a picture, or at least an opportunity to see everywhere on the Earth's surface about once a day as the satellite passes overhead and orbits around the Earth. And this is in contrast to geostationary satellites. Historically, there haven't been that many geostationary satellites with a specific air quality focus. This is starting to change. There are several new missions being launched, but the characteristic of a geostationary satellite is that it orbits above one area of the Earth. So it's always looking at that same area, but it's not, that means it's not looking at other areas. So you get more opportunities to view a single area, but at the cost of not being able to view other parts of the Earth. So that's a sort of a high level overview of the differences. But the commonality there is basically looking at a wide area simultaneously and getting sort of a very high level picture of air quality. And you can see kind of an illustration of that, the figure on the left. So, this is a composite of a day's worth of data taken over India, and you can see, at a very high level, what the conditions are in terms of, in this case, it's nitrogen dioxide concentrations. And I think another major advantages of using satellite data in this way is that it's fairly easy for people, even without an air quality background, to kind of interpret this image. They can see, oh, there are hotspots, there are areas of larger concentrations. You can kind of see plumes being formed and being spread by the wind. So that, it's fairly intuitive to kind of understand this type of data, whereas data collected by sensors on the ground at specific locations may need a little bit more interpretation by experts to kind of translate that to the general public. Another advantage, of course, is that these satellites, many of them have been operating for many years, if not decades, and this gives you a long data record with which to analyze trends over time, and that's kind of what you're seeing on the other plots on the right-hand side of the slide. So overall, the advantages of satellites for air quality applications is that they give these very high-level regional overviews of the situation. For disadvantages, for satellites, there's sort of, I think, two main sources of the disadvantages. Most satellite instruments that measure things relevant for air quality operate on basically reflected and refracted sunlight. So the light comes from the sun, passes down through the atmosphere, is reflected or scattered by particles and by different gases, constituents in the atmosphere, and that's reflected back to the satellite and measured by the satellite. And what that means is that basically that sunlight is necessary to take these measurements, which means during the nighttime you can't take measurements, and when the sun is blocked by heavy cloud cover or even heavy smoke cover, you can't take reliable measurements with these satellites. So that's a major limitation for taking these air quality measurements using satellite instruments. Another disadvantage is because the sun is, if the light is coming from the sun, passing down through the atmosphere, being reflected from the atmosphere or from the Earth's surface and going back up to the satellite, these measurements are reflecting the conditions throughout the entire column of the atmosphere between the Earth's surface and where the satellite's orbiting. And those conditions in that whole atmospheric column may or may not be related to what's actually happening at the ground level where people are breathing, which is what's most relevant for people studying air quality. So making those translations between the total atmospheric column and what's happening on the surface level is not always necessarily straightforward and easy to do. So those are the major limitations in terms of satellite data for air quality. So with those in mind, how can these data sources be used together? And I think this is sort of how I like to illustrate this. These data sources can be very complementary. And this is an example I'm taking from some studies we did in Kigali in Rwanda. On the left-hand side, you have a map of surface PM2.5 concentrations derived from a satellite data. And you can see it's providing coverage of basically the whole country. So a wide area spatial coverage, as I mentioned, is a main advantage of satellites. As opposed to, if you kind of squint, there's these 3 black circles, and those are the ground-based data sources we had access to in this study. So, only 3 points in an entire country versus an entire surface map over a country with satellite data. So that's the advantage of the satellite. But then if you look at the right-hand side of the screen, you have the temporal aspect of it. And in the red lines, you have the data collected by those low-cost sensors in Kigali itself, showing the daily cycle of concentration throughout the day. And I've illustrated with that blue box, that indicates the times of day during which the satellites, which were collecting the information used to make the plot on the left, were passing overhead. So that plot on the left really only reflects the conditions during a specific subset of the day, which in this case happened to reflect, at least in the city of Kigali, the times of day when the concentrations were lowest. So if you only had the satellite data to look at, you'd get a good spatial picture, but you wouldn't understand how that varied in time, which is actually quite important if you look at the temporal information we gathered from the low-cost sensors. And then at the same time, if you had only the low-cost sensor data, you could say a lot about what's happening over the daily cycle, but you could only really say what's happening at the specific points where you have those sensors. You wouldn't have any information about how that's related to what's happening elsewhere in the city or elsewhere in the country. So I think this is sort of at a basic level, this is how low-cost sensors and satellites can complement each other. The spatial coverage of the satellite and the temporal, high temporal resolution of the low-cost sensor can be very complementary to each other. On this slide, I've tried to give a general outlook of how low-cost sensors and satellite data can be integrated together. I've tried to kind of list examples of different case studies or application cases that you can do with those kind of data combinations, and I've tried to sort of rank them or grade them from sort of easiest to hardest in terms of the technical requirements and the data requirements. So the most basic level, I think a comparison of low-cost sensor and satellite data can be used to identify with the satellite data hotspots for potentially levels of higher pollution that can then be targets for follow-up monitoring with low-cost sensors. That's a fairly qualitative, but still very important thing that can be done with satellite data. Another more simple things to do is comparing spatial patterns and trends between low-cost sensor and satellite data. So does the low-cost sensor and the satellite, are they seeing the same thing? And if they're not seeing the same thing, why are they not seeing the same thing? A little bit more involved source apportionment, and this is a little bit nuanced, but at the basic level, you might think that if you're seeing certain patterns in your low-cost sensors, which are not being reflected in satellite data, then those may be very local patterns, which are not covering, they're not influencing a wide enough area to show up in the satellite data. Whereas if you're seeing the same thing in a satellite data and the low-cost sensor data, that might indicate there's a more regional effect going on. So that's a very simple example, but again, you can think of using these low-cost sensor and satellite data together to identify what things are happening locally versus what things are happening on more of a regional level. A little bit more technical now is quantitative comparisons. I have written here validation of satellite data products with low-cost sensors. That's not really, we wouldn't want to say we would validate a satellite product with low-cost sensors, but doing a quantitative comparison and saying, is the satellite data in agreement with the low-cost sensor data in this area? Then we might have high confidence in both the satellite and the low-cost sensor data. Whereas if they were in poor quantitative agreement, we might think that we need to look further into this because we may not have an idea of what the ground truth actually is. Similarly, or going the other way, using satellite data products to calibrate low-cost sensors in the field. This is still, I think, an area of sort of open research, but the goal for this would be using these satellite data products as a target to calibrate low-cost sensors to in the field. I mentioned earlier that low-cost sensor calibration is typically done with reference instruments, but where those reference instruments aren't available, you can't really do calibration of low-cost sensors. But if you had if you could calibrate against a satellite-based data product, which is available, almost everywhere, let's say, that would really open up the field to in situ calibration of low-cost sensors anywhere in the world. So that would be very powerful. But of course, there are many limitations to and technical challenges to that. And finally, the last thing here is a sort of a comprehensive integration of all the data sources together. So that's combining satellite data, low-cost sensor data, and of course, other data sources, which I haven't mentioned here, like model estimates, and of course, the regulatory monitors where and when they're available. It's just sort of a comprehensive, complete picture of air quality based on all the available information. So that's sort of the ultimate goal of this sort of integration. And I think for the rest of the presentation, I'll go maybe a little bit more quickly through some of the examples I put together. So just to illustrate some of the points I talked about in the previous slide. So this is the idea of analyzing whether satellites and low-cost sensors are capturing the same spatial patterns. This is just sort of an easy way example of how to do that would be take a satellite data product, overlay it on top of a low-cost sensor map, and then you can basically do a correlation plot of, are the concentrations at the ground sites matching well or correlating well with the concentrations in the column quantities as estimated from the satellite data. So here I'm doing an example for satellite aerosol optical depth, which is related to PM2.5, which is what's being measured by this low-cost sensor network. So, conceptually, this is very simple, but of course, there are a lot of nuances to this. Basically, what averaging period you're looking at. So are you doing this comparison for a single day? Are you doing it for a month, for a whole year average? Are you looking at the average throughout the entire day? Or are you only doing the averaging at the times when the satellite's coming overhead? That could be very important. Seasonal effects can be very important because they affect both the performance of the low-cost sensors in terms of the seasonality having an impact on the performance of the calibration, for example. Seasonality can also affect the satellite data in terms of there being more or less cloud cover during certain seasons, which might lead to there being more or less available satellite data, because as I mentioned, satellite information can be blocked by cloud cover. So, there's a lot of nuance to how you do this comparison, but at the very basic level, looking at is the satellite information and the ground-based data from the low-cost sensor network showing the same spatial patterns, or are they showing different spatial patterns? And if so, are those differences, specific to individual seasons, individual, sub-areas, sub-regions that you're looking at? Basically, why are the patterns different? It could also be the fact that, as I mentioned, the satellite information reflects the entire atmospheric column, which may or may not be well related to what's happening at the surface. So it might just be the case that in a specific application you're looking at, the satellite column information does not really well reflect what's happening at the surface. And that's of course important to know, but maybe a little bit disappointing. Similar idea for temporal trends, basically is the satellite data and the ground-based low-cost sensor network capturing the same temporal trends. And I've kind of tried to illustrate that here. So I have a question. What about resolution? Low-cost sensor data, much finer resolution. Yes. So yeah, that's an important point. I'll go back to the previous slide maybe for that. So you can see here in the map of the satellite AOD, you can kind of see the little squares reflecting sort of the sizes of pixels. And in this case, this was a fairly high resolution data product. So you can kind of see, you could see the variability in the surface, the AOD from the satellite at the top. You can see it sort of varying on a certain spatial scale. And you see from the map of low-cost sensors at the bottom, there's also some variability. And yeah, there's some nuance to that. That might not always be the case. The satellite data might not have a high enough resolution to actually pick out the differences you're seeing in the low-cost sensor data. You could have, a satellite pixel could cover 5 different low-cost sensors, each of which have a different measurement. So do you try to correlate that one pixel to the average of those 5 low-cost sensors which it's covering? Or do you try to pick out one of those low-cost sensors as being maybe most representative of that area as a whole and try to correlate the satellite with that? You would probably want to, test out both approaches and see which one works better. So yeah, that's an important point. The resolution of the satellite.
And is this satellite data freely available? And Swagata from India, and I'm the one who's asking these questions because we've been looking at this, thinking whether we could do something. And we've done the reverse thing, that you see satellite data, you see the trends, and then you use low-cost sensor for ground truthing, but for the reverse. And thank you. This is a very useful presentation. I'm sorry I barged in late. Yes.
No, that's a very good point. I didn't mention the resolution, but that's very important. In terms of being freely available, I would say yes. I didn't actually go through this on the satellite data slide, so thanks for reminding me. The satellites are obviously some of the most expensive instruments which you could use to measure air quality, but the advantage of it is they're typically operated by agencies like NASA, like the European Space Agency, which have sort of a mandate to, once the data are collected, make them freely available to the public. So, of course, some satellites are privately operated and they don't necessarily make their data available, but I think the main air quality relevant satellites that are operating today, the Aquaterra and Aurora satellites from NASA and the European Space Agencies has a couple of Sentinel satellites. So the NASA data are available. And I don't have a link on the slide, but I can put it in the chat a little bit later. But if you just search online, you can find these data sets freely available. And then there's another. Yeah. So yeah, I'll try to answer that other question in the chat with some of the other slides. I'll try to go through this pretty quickly since we're coming up on the halftime. So as I started mentioning, doing a similar thing on a temporal basis. So do the satellites and the low-cost sensors capture the same temporal patterns? And I've tried to illustrate that here, but again, there's a lot of nuance to that. Is the same temporal pattern at a certain time of day when the satellite's happening overhead, or is it the temporal pattern throughout the entire day? Are you looking at the temporal patterns, day to day? Are you looking at it month to month, as I'm showing here? Season to season, year to year? What time scale do you care about? This is also kind of where the resolution is important. So you're comparing over what area are you comparing? Is it just, one low-cost sensor compared to one pixel from a satellite that corresponds to that low-cost sensor's location? Or are you looking at a wider area with, multiple satellite pixels covering a city compared to a low-cost sensor network with multiple sensors covering the same city? So again, there's a lot of nuance to this kind of analysis, but the basic idea is, are you capturing the same temporal trends with the satellite and the low-cost sensor? And if you are, that's great. And if you're not, why not? And digging into trying to answer that why not question could actually give you some useful information about, is there a lot of local sources affecting your low-cost sensor network, which just are not showing up reflected in the satellite data? They don't cover a wide enough area to show up in the satellite information, things like that. So here's a couple other examples of other people's work. Again, this is sort of showing the qualitative comparisons as I discussed earlier. And this is particularly looking at a COVID-19 related lockdown effect. So on the left-hand side, again, using satellite data, they're showing sort of the spatial map of differences from one year to the next in terms of aerosol optical depth from the satellite, which is related to the surface PM concentrations. And you can see around the cities of Brazzaville and Kinshasa, the red indicates actually a decrease in AOD going from 2019 to 2020, which is, there could be various factors causing that, but one of the factors is, of course, the COVID-19 related lockdowns. And you can see the impact seems to be more intense in and around the city than it is in some of the surrounding rural areas, where the lockdown would sort of be less of an impact. And then complementing that with the low-cost sensor data on the left-hand side, showing, throughout the reductions, not just at the time when the satellite was measuring, but reductions throughout the day, although there were sort of more pronounced reductions in the evening. And that's information that only the low-cost sensor could provide because the satellite was not coming overhead in the evening. So that's one example. A little bit more of a quantitative example with CO carbon monoxide in Malawi. This is now actually comparing the low-cost sensors, which are in the blue and the orange box plots with their uncertainty ranges, against in the light blue, that's the MOPIT, which is a satellite-based data product. And in the yellow line, that's actually MERA2, which is a reanalysis, which what a reanalysis is basically a combination of an air quality model with satellite data historically to sort of nudge the model into better agreement with reality. So these are sort of now comparing a model low-cost sensor satellite and a sort of a model satellite combination. And you can see sort of the results of this study were a little bit mixed in terms of on a qualitative level, these data sources all kind of show the same trends, the seasonal trends and differences of CO concentration, as well as the sort of urban to rural differences in concentrations. But in terms of quantitative results, they actually disagreed with each other by fairly large amounts. The model or satellite were more or less consistent with each other, but they started to divert from each other during the biomass burning seasons. And then the low-cost sensor readings were much higher than the model or satellite-derived estimates. And there could be a couple reasons for that. As was mentioned, the resolution of the instrument quite a bit different. These low-cost sensors happen to be sort of right in the middle of villages where there was a lot of cooking going on. So those were very hyper-local sources, very close to the measurements, whereas the satellite and the model data would not necessarily reflect those hyper-local sources because they're covering a much wider area. And this actually gets back to one of the other questions, which is what is the ground truth in this case? And that's not necessarily clear. How do you define what the truth is in this case? We don't really know, in a sense, what the truth is, because we know the low-cost sensors themselves may not be well calibrated, and they're also reflecting a very local area, whereas the model and the satellite data themselves maybe have some bias in their measurements, but they're also reflecting a wider area. So I think in the case of this study, there wasn't really a conclusion in terms of what the truth was. But the conclusions they did draw basically was that we're seeing the same qualitative trends in all these data sets. So those probably are real trends in terms of seasonal differences. But basically, we need more study, we need more independent data sources to really zero in on what the actual true concentrations are. So now moving into more of a data integration rather than just comparing different data sources. And this was a study basically done with low-cost sensors in the Western US around California during a wildfire event. And basically what's being done here is on panel A on the extreme left is showing the correlation between individual low-cost sensors and the satellite aerosol optical depth, which is related to the surface PM2.5. And on an individual basis, the correlations were rather low for individual low-cost sensors. However, when you look at the area-wide map in panel H here, they took the area-wide aerosol optical depth and calibrated that to approximate the surface PM concentrations with the low-cost sensor data, which is what's shown in H and F. And then in the final panel on the very right, that's then compared to the quote unquote ground truth, which is from the regulatory monitoring networks in California. And that actually has, fairly good agreement there. So the idea here is that, even though we're using only the low cost sensor data and the satellite aerosol optical depth data, we're combining those together. We're doing a simple, I think in this case, it was a simple regression of the aerosol optical depth to the local low cost sensor PM2.5 surface level data. That simple regression derived a PM2.5 map in H, which was in fairly good agreement with the reference monitor data, even though the reference monitor data had not been involved in the creation of that map. Basically showing the sort of the scale advantages is that if you have a lot of low cost sensors in an area, you might be more willing to rely on that network as a whole than any individual sensor within the network. And if you have a satellite product which is covering the same wide area, you can really use those wide area properties to kind of really leverage the advantages of the low cost sensors in terms of having more data to really get a reasonably good final result out of that, even in the absence of any kind of regulatory monitors as the quote unquote real ground truth that you're looking at. So that's kind of an illustration of that point. A little bit more advanced than that, this is more of a near real time system where, actually I didn't mention it much, but there are geostationary satellites I briefly mentioned, which take sort of, instead of one observation per day, multiple observations per day. So this is illustrating kind of the combination of geostationary satellite data over North America with, in this case, the regulatory network over North America, the regulatory monitoring network, to derive sort of near real-time estimates of PM2.5 from these combined data sources. And there's no reason, indicated by the previous slide, there's no reason why we couldn't do the similar thing with a low-cost sensor network over a wide area. So, and then the last couple things I wanted to touch on were a little bit more conceptual, but the moving towards sort of the end goal of combining all of our data sources together. So taking a model-based estimates which cover a wide area, combining those together with satellite data, and then integrating that with regulatory monitors and low-cost sensors. So this is one sort of maybe conceptual idea of how that might work, where maybe you do a pre-calibration of your low-cost sensor networks against some reference monitors in an area to get your first sort of low-cost sensor estimate, and then you combine that with a satellite-derived map, and you do maybe an iterative cycle of calibration and validation where you compare your low-cost sensor network to the satellite data, maybe adjust the low-cost sensor calibration to better match the satellite data, and then adjust the sort of calibration factors which relate your satellite observations of the column to the surface concentrations. You might also adjust that a little bit to sort of iteratively make these two data sets sort of converge to one consistent representation of the surface air quality over a region. And that's, I guess, one of the last things I had was, that's a direction that I'm personally trying to go in with a project that was recently funded by NASA to combine global data sources like models and satellites together with local data sources, mainly regulatory monitors, but also including low-cost sensor networks where those are more available, and trying to sort of combine those all together in a sort of an open platform like Google Earth Engine is what we're going to be using in this project, as sort of an open data platform where all these data sources can be integrated together and made publicly available to support air quality analysis in different areas around the world. So this project is just getting kicked off. Hopefully we'll have more results on this in the future to share around with the ASIC community, but I just want to illustrate that to start off with. So I'm running a little bit short on time, so I'll try to summarize what I've talked about. Basically, for low-cost sensors, the major advantage, because of their low cost, they're increasing the availability of ground-based air quality information around the world. But a major limitation, which is still being addressed, is the need for locally relevant calibrations for these data sets to really get reliable data. And the difficulty of making those local calibrations in areas without access to a lot of regulatory monitors to validate these low-cost sensor data. For satellites, major advantage is wide area regional or global coverage, depending on the satellite. And a disadvantage is for certain satellites, they are limited to operate at certain times of the day when the satellite passes overhead. They only operate when there's sort of clear sky, daylight conditions, and they measure column concentrations, which is not necessarily the same as what's happening at the surface level. And then there are many opportunities to integrate these data sources together because the advantages and the disadvantages can be complementary. So, and this can sort of range in complexity to from kind of just qualitative comparisons of spatial patterns and temporal trends to regression analyses where you compare one data set to you sort of try to calibrate one data set using the other data set. Either simple linear regression or more sophisticated machine learning techniques can be applied to that. And then sort of ultimately, hopefully leading towards a full integration of these data sources together into a consistent air quality assessment. I tried to give a couple of case study examples of different applications for this around the world, just to illustrate some results of that. And I, of course, spoke a lot about the challenges being, I think, key challenges are having these data available. The temporal and the spatial scales, as we mentioned, do not necessarily match up between these two data sets. And, coming up with clever ways to work around those mismatches and figuring out what the correct average, spatial and temporal averaging schemes are to really get those data sets onto a consistent space-time scale to compare them is that takes a lot of thought and effort. And then finally, sort of in some of these cases, we don't necessarily know the quantitative ground truth which we're trying to arrive at, but we are maybe trying to iteratively get closer to that ground truth by looking at the satellite data, looking at the low-cost sensor data, and trying to figuring out, can they be brought into better agreement with each other, and maybe trying to zero in on the truth that way, but without like a trusted reference monitor, for example, in a specific area, or without some other data source, we might not necessarily have the ground truth in a given area that we're looking at. So I think that's what I had for today, and hopefully there's a little bit of time for questions.
Yes, there is. Thank you so much, Carl. Appreciate that great presentation. To everybody out there, yes, if you want to share any questions you have in the chat, we can read them and have Carl answer them. For anybody that joined late, just note that we did record this session and we'll post it online later for you to review.
Okay, so there's a question about talking about the use of satellite data to approximate emissions from sources. That's a good point, which I didn't really go into, and frankly, I'm not an expert on that application of satellite data, but it's certainly one that can be used. The basic idea there is to look at the, you can see, maybe I'll go back a couple of slides. So you can see, let's say in the map on the left here, you can see a couple of, red points showing up, which some of those are actually individual power plants, let's say, which you can zero in on. And you could sort of look at those power plants, make some assumptions about or use some other information about the meteorology, the winds, look at those concentrations, and basically estimate how much is actually being emitted from the source based on how much is visible in the atmosphere in close proximity to that source. As Subbu said, Dan Goldberg is much more of an expert on this than I am, and he's done some work on point source emission estimates, I think specifically for NO2. So that's a great point. Subbu says, talk about the level of technical expertise and skills required to exploit satellite data in combination with sensor data. What does the end user need to know programming language? How much time do you need to spend learning the tools? That's a good, so that's a good point as well. So there is, to my knowledge, there's not really a one-stop shop to do this kind of analysis. It's still very much sort of a research level thing of, combining satellite and low-cost sensor data together. So each researcher sort of has to devote quite a bit of time and energy to sort of understanding this. I did not put the slides here, but maybe I can work on putting it in the chat later. And it's actually mentioned, the link on this slide specifically, which is kind of what I would put in. So NASA specifically has what's called the Applied Remote Sensing Training Program, or ARSET, A-R-S-E-T. Their goal is basically to make trainings related to different satellite data products that NASA has. They also give trainings for other data products that other space agencies put out. But it basically gives an overview of the satellite data product, and it goes into quite a bit of technical detail about the individual satellites, the capabilities, limitations, how to get the data. Thank you for the link in the chat. And including sort of, examples of how to access the data, how to interpret the data, and code, snippets of code. They have on their website, they have recordings of past trainings, which you can watch, and they'll also include the code that they use in those trainings to access and to interpret the data. So I'd recommend that as a good source to get started if you really want to learn about using the sensor data. So I'd say that's one aspect of it. And for that, in terms of programming languages was part of the question. I typically use Python as my language of choice to load and interpret satellite data. You can, of course, use other things, but that's just what I use. And that's a lot of the trainings from ARSET also use Python code examples. And then the final thing I'll mention, I very briefly touched on it when I was discussing the project that we're starting up, but we're going to be using Google Earth Engine for that. And the main reason for that is it is, a single place to go where a lot of different data sets from a lot of different sources are all put together in one place. And they've done a lot of the work behind the scenes in getting those data sort of aligned to the same sort of, latitude, longitude, basically, interpreting sort of like the spatial allocation of the data to different latitudes and longitudes, and getting all the data sets sort of so that they're on the same latitude, longitude grid, and they can be sort of compared with each other directly. So that kind of, it's, for some people, maybe that's a little bit of an easier way instead of learning a programming language that's a little bit more visual. But there's still quite a bit of programming there. So I would say, I guess the short answer would be ARSET training for NASA data products and other kind of satellite data products to learn how to access the data. And then I would say that there is still this limitation of there's a lot of expertise needed to access, load the data, and do quantitative analysis on the data. So let me see. All right, so the next question. Analysis or models can help bridging satellite land use regression or regional air quality model integration. Yes. So yeah, so the land use regression is one example of that. Yeah, the question is, yeah, basically how to integrate the low-cost sensors and satellite data is more technically. I just mentioned generally regression. Now, regression is a very wide topic, but basically the idea is to take the satellite data and take various other information, for example, land use data, which is used a lot as sort of, covariate information or other important information, and create a regression model where you take all that information and try to estimate a known surface level air quality, either from a low-cost sensor network or a regulatory network if you have access to one. Yeah, there are a lot of different ways that you can go about doing that. I wouldn't want to recommend there's one way to do it. There are many different ways to do it. I think including data from land use regression in terms of what the actual land use is in different locations can have a lot of value in those types of models. That's been shown through the research. And regional air quality model integration In my case, I use a lot of global air quality model integration, but you can do the same thing with a regional air quality model if you have access to that. And basically that model can provide you with sort of a first estimate of what's going on. And then estimate can then be refined with the satellite data and with the local data. So for example, one of the issues with the satellite data is it's measuring a column quantity, and you need to relate that total column to what's happening at the surface level. And a model which simulates the entire atmosphere will have that information kind of output as part of the model. Now, it may not be getting the column accurately, and it may not be getting the surface accurately, but maybe it's getting the ratio of the column to the surface accurately. So if you use that ratio and then you use the column from the satellite, you might be able to get a more accurate estimate of what's happening at the surface than using any one data source independently. And that's kind of the idea behind this project. So more information about the project, collaboration with Senegal. Yeah, so we're getting started. And I did show Senegal in that picture. So let me just go to that slide quickly. So in this project, which we're getting started, we're kind of still in the phase of just developing the system on the back end, but very soon we hope to reach out to our end user cities who will be the ones who are helping us pilot the application of this new tool that we're developing. One of those cities is Dakar in Senegal. We have an agreement with the Ministry of Environment and Sustainable Development there. And we'll also be working through the UN Environment Program. Sean Kahn at the UN Environment Program is sort of our liaison or our contact he's done a lot of work with them in the past, and he's going to help us kind of get in touch or, help us to help them get this new tool kind of integrated into the system that they're using, which will, ideally be a good tool for them. And
I want to jump in here, Carl, real quick. We're at about time. However, if you have time to keep answering questions, we can keep going. Yeah.
Okay. I've got some time, so I'll try to keep answering these questions, but
great. And then for anybody else that has to jump off, I do want to just remind you we're recording this session, so we'll have the recording out in a couple hours so you can review any questions missed. But go ahead, Carl.
So that's that question. Okay, next question. Has there been a method to directly compare satellite data with ground level measurement for regulatory purpose? For example, how much of an AOD unit corresponds to equate with the WHO PM 2.5 limit? To my knowledge, it's a little bit, for exactly this reason, it's a little bit tricky to use satellite measurements for regulatory purposes, because the satellite's measuring sort of a column quantity, and the regulations are all about what's happening at the surface level usually. How much of a unit of AOD measured can be equated with the WHO PM 2.5 limit? Yeah, that would be great if we could provide an answer to that question, but I think what the research shows is it really varies a lot by location, by seasonality, by the composition of the aerosol can also have an impact. So developing sort of one universal relationship is probably not very practical, but at a more local level, we can maybe try to figure out what are typical relationships, and I think maybe the more practical, at least in the shorter term, thing to do would be to try to develop a locally applicable tool which just does a good job of translating the AOD in a specific focused geographical region to the surface level PM 2.5, verify that works well in many different seasons and many different weather conditions and things like that, and then use that as kind of a supplement to the ground-based regulatory monitoring, which can have a wider area coverage. And if it can be shown that this satellite-derived product is in very good agreement with the regulatory monitors where they're available, that would then provide some stronger evidence for and stronger justification for the use of a satellite-derived data product for more of a regulatory application. There I think at that point you probably start running into the legal issues of, how is the regulation defined specifically? Does the regulation require, a lot of these regulations specify the methods by which the compliance with the regulation is to be assessed. And, satellites are probably not one of those methods. So that requires like the law then be changed to allow a satellite-based method. So, but I think, the sort of the scientific preliminaries to getting that is to really develop a good method for basically, determining how much of a unit of AOD can translate to surface PM2.5, probably for a specific area, for specific certain periods of time, and really verifying that that's performing well, and then from that you can sort of move on. Okay, moving on to the next one. Share your thoughts on source identification for PM by using low-cost sensors. I understand it's not straightforward. Looking at the mass sensor, and have a large low-cost sensor network covering urban rurals, and established methods to really separate out the local versus the regional contribution. I'm not. I wouldn't say unfortunately that there's an established method, but I think what I kind of alluded to is one way to do it, where if you look at a sort of a satellite-based picture, at least qualitatively, you can see what the trends are. And if you're looking at the satellite-based picture, that's really going to reflect mainly the regional things that are going on, whereas your low-cost sensors will reflect both the regional and the very local effects. And that could be one way to tease out those two effects. Let me see if I can think of any more useful comment related to that. So again, like source apportionment is not something I've done a lot of with these kind of applications. And as Subbu mentioned, sort of the emissions studies are another aspect which I haven't looked at a lot. Unfortunately, I don't have a lot useful to say about that, I guess. But that would be sort of my first guess would be to do, again, more of a qualitative analysis, but to just say, okay, this is what the low-cost sensors are seeing. This is what satellites are seeing. When do they agree with each other, and when do they disagree with each other? And really looking into when the agreement's happening, that could indicate that it's really the regional, not only the regional maybe, but more so the regional effects, as well as sort of, it depends on how you define local and regional, but any sort of, let's say, city-wide effects that are impacting your whole network and the satellite data at the same time, versus in times when they disagree. Do they disagree? Maybe some of your low-cost sensors agree with the satellite. The more sort of quote-unquote background sites agree better with the satellite during certain periods of time, whereas other sites, which may be more impacted by local sources, are agreeing less well with the satellite data. So that would be sort of my first way to sort of tackle that problem. Some good discussion. Is it possible to identify major sources in a region using AOD data? Let's see. I wouldn't. There's certain things you can do. I would say in that direction. So combining, let's say, AOD data with some local knowledge of what's going on in a region at a given time, it's definitely possible to pick out certain things like wildfires or like agricultural burning. For example, if you happen to know where sort of there's an agricultural region, and when the agricultural burning is happening, you can look at the satellite images and you can usually see fairly clearly, okay, the agriculture burning starting, there's smoke coming from this region, and then it's being spread to certain other regions, and it's impacting those regions. So that's a little bit more qualitative, but you can definitely look at those kind of trends over time. Yeah, I would say so. For sources like the AOD data alone is not going to give you kind of what the source apportionment would be, but if you look at the AOD data and you incorporate in some information about seasonality, and what, and if you look at sort of the wide regional spatial picture, to kind of, if you can just visually see where those AOD plumes, let's say the smoke plumes, are coming from, that might be able to give you some information about what the sources are. And then Subbu linked an article about wavelet decomposition. Yeah, I think that's a good approach as well, going into it a little bit more quantitatively. In estimation of PM 2.5 from satellite and vice versa with the ground level locus, how can we estimate PM 2.5 and AOD? Can you give details about the model, code, and Python parameters used? Yeah, so that's a good point. I think one of the places I would start with that is this paper. This is from Pawan Gupta, who's also at NASA, who did a lot of this work relating AOD and PM 2.5, and I think this is a pretty good paper, kind of, giving a nice summary of the method. So, and I think in this approach, he used a very simple linear regression to relate the PM 2.5 from the low-cost sensors and the AOD from the satellites. And I don't recall off the top of my head whether he used any kind of covariating factors. I don't think he did in this study, but that would be sort of a next step, maybe, to look at temperature, humidity, land use information, things like that, as sort of covariating factors. And in terms of in terms of the model and parameters, and then for the code, for this, I would also kind of look at the RSET trainings that I mentioned. I don't recall off the top of my head which training this was, but in RSET trainings, we've done some examples where we take, and he's actually done this in Excel, which is a very simple way to do it, but obviously you can implement that in any kind of coding language if you can do it in Excel, where he's taken sort of the AOD from a specific location, the PM 2.5 from the same location, and he just made a simple regression with those two. So that's again, through this paper, and then through if you search in the RSET training for, relating satellite data and ground-based air quality. There are several trainings related to that topic, and they will have some code examples as well. And then some internal discussion. Yeah. So, yeah, following up with what Subbu said, yeah, the wavelet decomposition. Again, that's looking at the different temporal aspects of the data to decompose into the different sources. And I guess you'd have to be a little bit careful with that in terms of what's, with low-cost sensor data, if you have sort of a regular hourly data, that's very useful. That fits pretty well with wavelet decomposition. If you try and incorporate the satellite data into that as well, you may have to be a little bit more nuanced about that, because the satellite data will not necessarily be at the same, you won't get, depending on where you are, depending on what satellite instrument you're using, you won't really get those hourly data. You might get a daily data. You might get maybe every other day if there's a lot of cloud cover. So handling sort of the missing pixels and the lower temporal frequency might be a little bit more challenging, but I think, yeah, basically the idea of wavelet composition is a good framework to use to look at the source identification as well. Yes, thanks, Subbu, for that. You try using MERIT-2 reanalysis. So that's I guess something I didn't mention, but in models like MERIT-2, which is a reanalysis, which is a combination of model and satellite data, the different, let's say the aerosol constituents are, all separate. So you have sort of biomass burning aerosols, and you have sort of sea salt, and different kind of sources of anthropogenic aerosols. So yeah, looking at a model, of course, the model, the model is only really reflecting what the inputs for the model are. So if certain sources are not included in the model, those sources won't show up in the model output. So if you're doing your source apportionment based only on the model, you may be wrong in that sense. So my suggestion would be, yeah, you can use a Merit2 reanalysis data, identify the major sources in that, and maybe also do some verification. So compare, let's say, the ultimate PM2.5 value from your Merit2 analysis to your, if you have a low-cost sensor or regulatory network, ground-based measurements of the PM2.5. You can also compare the aerosol optical depth from the Merit2 model with the aerosol optical depth from a satellite. And you can kind of just use that as a sanity check to verify, is the model really reflecting what the satellite and what the ground-based measurements observed during this time period? And if so, we could maybe have more confidence in what the model is saying are the sources that contributed to those concentrations. So that's a really good point. And then Subu, yeah, that's the paper I cited earlier. And yeah, it does have a link to some of the codes we used for that. That analysis was, I think, also just based on a simple linear regression from the aerosol optical depth to the surface PM2.5. It was a little bit nuanced just in the sense that the regression would vary by, I think, by seasonality, because we did see like there was a big seasonal differences in what those things are. But that's one thing you can use. Okay, so I think I got to the end of the questions in the chat. And I guess I'll ask Sandra maybe. I can put the slides on the. I can put the slides on the website maybe.
Yeah, if you want to shoot me an email with the slides, I'll add them to the website along with this recording so that people can check out the slides further, click on any of the links as well. Yeah.
And maybe I'll add 1 or 2 links that came up based on the discussion. And that's my email. Definitely send me an email if you want to chat further about this.
Perfect. Thank you so much, Carl. Really appreciate you taking the extra time to answer everybody's questions. Yes, so I put Carl's email in the chat if you wanted to send him an email and connect further, and we'll put up the slides in the recording as well. Thank you, everybody, for sticking around for the presentation and providing a great conversation in the chat and with Carl asking follow-up questions. We appreciate it and your time. So thank you, Carl, and I hope everybody has a great rest of your week.
Thanks, everyone.
Thanks. Bye-bye.